My name's Micah Johnson, and I spent the last year developing a SnowEx database. And the goal with this database was really to just try to hold as much SnowEx data as possible. And it's really important because there's a lot of different data sets and a lot of different headers and tons of information that is useful to individual data sets, but is often challenging or cumbersome for individual researchers to do work with. So it's kind of the impetus for this database. If you've ever been presented with some new software technology and somebody comes along and says, this is the greatest and latest, you got to use it, and then 2 months later it's totally outdated, I don't think this is that. But I understand that feeling, and I understand the feeling that new technologies often feel like a barrier to the work that we're trying to do. And I'm going to try to convince you during this that this is going to enable your work and not limit it. So what we're going to try to cover in our hour here is kind of what's in the database and how it's structured so that you can navigate it effectively. And then we're going to start forming some queries so that you can pull the exact data sets that you want. We'll go through a couple of examples. We'll talk about how to export some data really quick. And then I'll give you a couple of resources on how to bring all of this into QGIS. To kind of emphasize why a database, I came up with this line, dude, I'm into pits, not bits. What gives? If I were in your shoes, I would be annoyed that somebody was trying to pitch me on data that I've collected that's now stored behind some brick wall called a database. But the main reason is really that it standardizes a lot of the data sets. It allows us to cross-reference any data set and instruments and any kind of associated metadata. There's a ton of geospatial functionality that comes along with this that allows you to offload some work from your computer onto the database. A lot of the stuff that David Sheen showed can be done on the database before you even get your data down. And the other thing is it's ready for use in Python code. You can just start using this stuff right away. And then a big thing that's come up, I think, in any kind of data-rich science setting is provenance. The cool thing about this database is we've spent a lot of time making sure that if the database were to explode, we could rebuild it tomorrow, from pulling data from the NSIDC all the way to uploading it onto the database. And I think that's really important because a lot of people, myself included, will do research and then maybe a couple of years later go back and look at their scripts and go, man, I must have done something. There's an extra step in here I don't see. And then this kind of database is ready to use for in any kind of GIS software. And we'll talk about QGIS at the end. So the long short of this is that you'll do a whole lot less wrangling and a lot more crunching. So what is the database exactly? It's a PostgreSQL database with a PostGIS extension on top of it. And the PostGIS extension on top just gives that GIS functionality. Postgres databases are really common in the software industry, and they're really well supported. It's an open source software, and it makes Googling things on Stack Overflow super easy. This database supports vector and raster data and those operations. And then, like I said, we get all these functionality, like being able to say, I want all the points in a circle at this location. You know, that kind of functionality is built into the database. For right now, we've limited the data to Grand Mesa, and all the data is converted into EPSG 26912, which is UTM Zone 12 and NAD 83. But the specific data sets that are in there, we have all the snow pits from 2020, the manual snow depths from 2020, and I think there was like 37,000 of them. It's a really rich data set. We have all the micropenetrometer profiles. Those profiles are pretty big, so that we've subsampled them into the database every 100th point. We did include the original file name for them so that you can go find them if you want to do more research with them. We have the snow depth and SWE rasters from ASO. We have the full GPR data set for Grand Mesa. We have all the pit sites and the camera-derived snow depths. We added a DEM just to make people's lives easier. Made mine easier with this figure below. And then we tried to include as much associated metadata as possible. So just to give you an idea here, the this is all the data we could visualize at once over that DEM that's in the database. These little dots behind the scene are the centroids of the tiles that are in for each raster. So we have the UAV SAR data set in there. And anyways, it's a really cool picture, but it shows, I think, the power of the availability of this data. This is an example pulled off of the SnowEx repo. So if you want to go look at what it took to make this, all that code is available to you. So maybe you're not totally convinced yet, but if you're enthusiastic about that, maybe you want to know how to get at this magical box of data. So the good news is that this is a SQL database. And if you know SQL, then you can go at it and get at all this information without ever touching Python. Or any other language for that matter. R, I know, has a database connector. MATLAB has a database connector. All these things would be available to you. The other alternative is we've written a package in Python for interacting with this database, specifically for maintaining and accessing data. That's what we're going to focus on here for this presentation. And you'll see there's a little bit of play back and forth, but you'll get to see that I think you'll find that it's more useful. So to get at this, you really just need these lines. These are the lines you'll use for all of Hackweek. So anytime you want to get at the database, you'll want to use these 3 lines at the very least. We're all going to use the same user and password. It lives at this IP address, and the database is called SnowEx. When you import this function getDB and apply it using this string for the IP address, you'll get back 2 methods to interact with the database, the engine and the session. I think maybe some of the issues that folks have been having today, if you're like me, you're working on a laptop during these presentations. And so jumping back and forth between the presentations and trying to execute the Jupyter notebooks is a little tricky. So what I want to do is I'll run through things and then offer you a chance to execute those things to see if things make sense or if there's something you want to try kind of quickly. So when I execute this, not a whole lot happens, but I have these engine and session objects. To use the engine object, if you're familiar with SQL, the best option for you would be to use this if you wanted to still dabble in Python. You can just write out your SQL query and then get at it. And the whole point of this is just to show you how fast we can get to data here. So when there we go. So what we're going to do is select all the unique site IDs from the table sites. We're going to execute that query here, and this is what we get. This is all the site IDs that Megan went over yesterday and how they are labeled. So right away, you have the power to filter on data just using the naming convention of the site IDs. The other alternative we can use is using the session object. And this approach uses something called object relational mapping, or ORM. And that's an important acronym for Googling, because that'll help focus your results on things that relate to this. And this is the method we're going to focus on for this tutorial, partly because if you use this method and you adopt it, you won't have to learn any SQL, which is pretty amazing, I think. So here, what object relational mapping does is it maps a class to the database, and specifically a single table and row. So what we're going to do here is we import site data, which is going to be a reflection of our sites table. And we're going to call this, we're going to ask for the site IDs and ask for the unique ones. And then when we execute that query, we'll get the same exact thing as above. This may feel a little cumbersome at first, but I think when you get into the nitty gritty of dealing with geometry objects and getting into rasters, you'll find that the ORM method is really, I think, better. But if you're a SQL master, then it probably won't be. So really quick, let's talk about what object relational mapping actually is and what it's doing so that it's easier for you to use. Since we can use this just in pure Python, and all these tables get mapped to a class that we've defined. And the beauty of it is that each class has an attribute that is mapped to the column. And an attribute is just a piece of data that's attached to our object. So when the class gets instantiated to the table, it now has an attribute for every column that exists. So, and the important thing is that everything will be in the correct types, which is really, I think, a huge piece. Because even if you were to read this data in with a CSV, you would still have to spend some time casting things to the correct types. So if we take this little table here that I made, this is actually a small snippet of the sites table that we have. And let's just say it's this big for right now. To do this, to query this table in object relational mapping, we would simply import our site data table. And then we would, if we were to ask for all of it, we would get back a list of these objects. And then these objects would all have an attribute associated to these by each row. So if we wanted to see what the ground roughness was for the first item in the row, we would ask for the 0th item here and then do dot ground roughness. And that would give us rough, which matches what's in our table. So if you wanted to do this for other things, you would just simply swap out this for another column name. And then if we wanted to get at, say, the second row, we would just put in 1 in this list. Okay. So I just showed off how to get at the database pretty quick. And we saw a couple of methods for interacting with the database. One kind of better suited for SQL masters, and the other suited for people who don't know any SQL. And then we just kind of crash coursed into object relational mapping. So I want to pause for a second and allow for quick questions about object relational mapping, or maybe this figure up here. But next, we're going to go into the database structure and talk in more details about what's actually in the database and how it's built. I don't see any questions in Slack that I noticed. OK. Whoops, my lights went off.
Oh, well, we're getting somebody typing in just maybe another minute or so, Micah.
OK, perfect. Yeah, so eventually we will have, Ross asked if all the data is going to be eventually available. Eventually, all the data will be in there. That's the goal. But we limited it to Grand Mesa just to prevent people from querying a ton of stuff. OK. Oh, there's some more typing. Perfect. Oops. On an unrelated note, my internet provider is having a national outage, and I had to run to Boise State to switch internet at the last second. So if the lights turn off, it's because I'm not used to the motion sensor lights. OK, I think I'm going to jump into the database structure. CHP's typing. I'll jump back to that here in a little bit. OK, so the number 2 here, there'll be a little more interaction if you're interested in trying to run some of these blocks. But again, I would try to follow along with the visual, and then we'll go back and have some chances to mess with things yourself. So to navigate this database, you'll have to learn how to at least discover the structure of it. What we're going to do here is we're going to access the database using the library, and then we're going to query to see what tables exist. And then we're going to see what columns are in those tables individually. And then we'll get to see what data sets and other things are available to you. So again, here's our 3 lines of code that you'll use all the time. When we execute that, we just have access now to our engine and session objects. And here we're going to use the engine just to get the SQL table names that live underneath. And what you see right away is we have 5 tables here. The spatial reference system table is not one you want to mess with. So just ignore that. That just manages a bunch of GIS stuff for you behind the scenes. The ones we've made and store data that matter to you are layers, points, images, and sites. From an object relational mapping standpoint, or the ORM, we can import all of those in the same exact way using layer data point data, image data, and site data. And all this lives in the data submodule of SnowEx SQL. So if you want to see what columns are available to you, because there's a lot of them, we have a handy dandy function to get all the attributes from a table class. So what you can do here is import point data from our data submodule, and then import this get table attributes function. And then you can apply that to the point data and get out all the columns that are available to you. And this is important because if you want to learn how to get back specific data from certain tables, you'll need to know what these columns are underneath. When you do that, you'll get this nice list here, and this is just printed out here with this fancy way of doing that. It's not that fancy. And what you can see is there's a bunch of stuff. One of the things, in terms of provenance, all the data that's been pulled from the NSIDC is cited correctly, or at least has the information for you to cite it correctly. So it has when we accessed it, and if it's a published data set, it has a DOI associated. There's an instrument, a lat long. There's a geometry object, which is what the computer is reading for knowing all the GIS stuff. And yeah. I don't expect anybody to memorize these. In fact, I frequently have to look up how many there are or what the names are. But I'd encourage you right now, take a chance, go to your Jupyter Hub, execute these blocks, and then I'd encourage you to go through all the tables right here. So change point data to, say, layer data, and you'll have to change it here too, and then exercise it. And just take a look at what columns are there. And then I'll give you a couple minutes to do that, and I'll go look back at Slack to see if there's any questions. But take a look at what columns are in there, what might be of interest to you, or what you think maybe would be useful in there. Those are all really important things for making the database more friendly to the community. So take a couple minutes to try those two things, or try the other database, or the other tables, excuse me. Yeah, thank you, Joe, for answering Paul's question. This is an important thing, and I don't want to put off any kind of sense of skill, because I'm not a database expert by any stretch. I am an expert in this database, so I built SnowEx SQL, the Python repository, as a way for us to build and maintain the database, but also I threw in tools for us to be able to access and query it. So it's really just, like Joe said, a framework that allows us to do stuff. Okay. Has everybody had a chance to try some of these? Give me a thumbs up, or you can wave your hand if you're still thinking. So I want to talk a little bit about why these tables exist and kind of what's the differences here. So the way we've tried to organize this data is that the point data table would contain all data that could be represented with a single value and a single location. So you can think of this as manual snow depths, or the GPR at its smallest data point is just those two things. So point data contains all those things. Layer data is considered any data that had a vertical component to it at a single location. So you can think of density profiles from a pit. They have value at each depth as you go down into the pit. And so that's where data like that gets stored. Hand hardness profiles, SSA, snow micropenetrometer stuff lives there. And then in the image data, that's where we're keeping all of our raster data. And then the sites data contains a lot of the metadata for the pit data. We tried to include those all together at one point, but it was just too burdensome on the database. And so we left it as a separate table to allow you to grab extra information. Things like ground roughness, sky cover, temperature, what time it was done, etc. Okay. You can also go back and read about this. This is the documentation for the whole repository. And all that information that I just rattled off exists here, along with the column names and kind of what that column contains. So kind of a bonus step here is learning to help yourself, which I think is the most important thing whenever you're trying to grapple with some new, especially software technology. We spent a lot of time making documentation for the repository and the database itself. And you can go there just like we did for the database structure, but you can see examples. You can look at the database structure. You can look at data notes. Anything that had some kind of modification from its original state and then went into the database is mentioned in here, ideally. Most of it is. Then you can always go to the repo and ask questions there with issues. SnowEx SQL is built on GeoAlchemy, which just brings the GIS functionality to the database in Python. And so if you need any questions relating to GIS queries, that's a good place to start. SQAlchemy is kind of the underlying structure of everything, and it's just mapping Python to database queries in general. So if you have just some general filtering ideas or querying, that's a good place to start, and it's heavily used in software. PostGIS is another place to go look. These are SQL commands and functions, but they all get mapped into the Python world, and we'll talk about that in a little bit. But you can see what your options are here. There's just tons of them, piles of it. So it's a good place to get starting for what kind of functionality you can have really quick. And then finally, I made a cheat sheet, the things that I think were really useful while I was building some of these examples and testing. Just talking about the database tables and some querying techniques that I used, and then some useful functions you'll find later. So all that's available for you. So to recap here, you should be able to go back and find a way to find the table names and know that layers and points and image data and site data are all the important ones to you. You should at least know how to get back to that function to get the table attributes so that you can see what columns are available and you can filter on those. And then you'll have some resources here. Okay, so we're going to start jumping into the meat of this, which is forming queries. And I think that's the part that everybody's really interested in. And there'll be some chance here for you guys to try some things as well. Okay, so it's handy to have your cheat sheet if you're messing around with these or you want to try your own thing at some point. But just like always, we're going to get our database connection in the same exact way with our engine and session object. When I execute that, I'll have those. And then depending on what data you want to work with, you would import any of these or all of them. It doesn't matter too much, but it does matter that it exists for you to query it. And then every object relational mapping query is going to start with this query function. So we'll take that session object that we get back from here, and we're going to query. And what we're going to query is anything we want back. So here, for instance, anything that goes in the parentheses of the query function is what we expect to get back. So when I execute this, I don't have my connection, I don't think. Oh, something's not right. Well, maybe similar to some of our Jupyter Hub issues, we might be having some database issues because I've never seen this error before, but I'm thinking that we have too many connections maybe. If this is the case, we have everything rendered online and we can just go through that like we've been doing. And I think I'm going to jump to that also. Hopefully that's not too jarring. Oops, I went back too far. So this is under tutorials, day 2, and then SnowEx database. and we are on forming queries. Okay, sorry about that. I wondered if that was going to be an issue because we've never had a lot of people querying it. Okay, so when we query this point data class from the table, we're just saying we're going to just grab one of them. And what we get back then is a point data object in a list. And that would have printed here, but we don't have that now. So what you end up getting is just an object that represents one row of data from the table. And it's a pretty simple example, but it's important to realize as we move on what you're actually getting back. And these are all objects that are mapped to the database. If we wanted to change the number that we'd get back, we could move this number to 2. And we'll talk about filtering here in a second. But if we wanted to, say, not grab a whole row and grab certain columns, we could do point data dot and then any column attribute. And you could comma separate those in this query parentheses to get back any set of data you want. And we'll see a little bit of that in a minute. So to filter anything, I mean, using limits is great, but it doesn't allow us to do a whole lot besides just see that the database works. And when we want specific data sets, which is really the point of the whole database, we use this filter function. So here I form my query using layer data. And so this is just saying I want layer data objects back. And then we're going to take this query object, and then we're going to do a dot filter on it. And you can kind of carry this around like this, and it doesn't get executed until you run .all. I think this is a really nice way to do it because it's a little more readable, but you could definitely append this onto the end and just keep going with filters. In this case, we're going to query the layer data table, and we're going to ask for the density profiles back. And then we're just going to limit that to protect ourselves to 5 layers. When we get that back, you'll see that we just get a list of layer data objects. And each of those has all the attributes in the rows that we need that are mapped with the object relational mapping. Okay. If you want to keep filtering, you can just keep dot filtering on a query object. So you could have 100 of these lines if you wanted doing different things. Eventually, you'll probably out filter your data and you'll just get back an empty list. But there's no reason you can't filter on a filter. The other thing that comes up a lot is, if you just want a single column or a single attribute of the class back, you can always just pipe that into here. And just remember that anything you put into query is what you're going to get back down here in this returned list. The other thing that I get asked a lot is, how do I know what to filter on? There's stuff in there, and I know there's valuable information, but I don't know exactly what that information is. And so what we can do is use distinct as kind of a exploratory tool, which just says, give me all the unique values for this data that exists. So for this query, we're going to ask for layer data.type, and then we're going to ask for the unique data types that exist in there. When we ask for that back, for layer data, we get sample signal, force, grain size, density, reflectance, permittivity, all these things. And this is how you would then start to filter, is use these keywords to filter in these tables. Same thing with instrument. We can do layer data.instrument.distinct. And then we get back a list of all of our layer data instruments. I think Megan mentioned yesterday that manual measurements, things that were done with the hand, for instance, hand hardness profiles, were left as none. That's something we'll probably change to a string that says manual. Anyways, you can do this with any of the attributes that exist in the database tables. So a big one that comes up is dates. I use dates a lot for just trying to see what dates are available for this query. And you can do these with more filters too. So if you wanted to say what dates are available for density profiles, you could filter by layer data.type equals density, and then do distinct on the dates if date was in your query return spot. Okay. All right. That's a really fast and not interactive introduction to filtering and querying on the database. I guess at this point, are there questions? And are people feeling a little bit behind? Or I don't know how many people are able to actually use the database, but I'm not at this point. So certainly throw out some questions. Yeah, Anthony said one thing to note is that we are somewhat temporarily hosting the database. Yeah, it hasn't been tested for receiving large volumes of queries yet. We'll leave it just like a minute or two for any kind of questions that people are thinking about with forming queries and filtering. Yeah, sorry, Jessica. I'm also having issues with it. I think we just have probably too many people connected to it. This is something that hasn't, unfortunately, been tested with a large group. But I'm happy to answer questions about it as you start to tinker. And then there's a bunch of examples on the GitHub repository ranging from really complicated to really simple. I know that a lot of the tutorial leads have been able to grab some of those and get started with their stuff. So that might be a good starting place since we can't really try it right now, unfortunately. I'm sorry about that. HP asked, where would UAVSAR showed up? It's not under instruments. The instrument is,
I think it's UAVSAR team, JPL.
That's under the instrument?
Surveyor, sorry.
Oh yeah, yeah, you could filter by surveyor. I think it's UAVSAR, INSAR. I can't remember. Another way that you could answer some of those questions is you could go and look at the upload scripts and see what instrument I used. I'm trying to remember if that's actually in there. This is very much a living database. So as you find things that maybe are a little quirky or not the way you expect them, we can totally change them. We've made changes to the database over the last week on naming conventions and things like that. Okay. So I think probably the best thing at this point would be to try to do an example, although it'll be me droning on about database querying. This will be a good place for, I think, everybody at some point to go try this if we can get the database actually accepting more connections. So here's what we're going to do. We're going to visualize some of the snow depths that were collected during 2020. When we surveyed everybody for Hackweek, this was a overwhelmingly data set that people were interested in. So again, don't forget your cheat sheet if you want to use that to just see what is happening or things that are useful. We're going to connect to the database like we have been. And then, oh, here, let me get back to, I get confused between the Jupyter Hub and the website. Okay. We're going to connect to the database. And then we're going to build a query, and we're going to filter by data set and date. So here's our typical database access function. We're going to get at our points data table because that's where snow depths live. And then we're going to introduce another function here. This is a handy dandy query to GeoPandas function. And David just talked a little bit about GeoPandas, but essentially it's a really awesome data structure that you can use in Python to visualize GIS stuff. And it's great. What this function will do is take your query that you build and then execute it and format it right into a data frame for you. So it's already usable. We're going to import the built-in functions date so that you can build a date object to filter by. And then here's our connection. So we'll get connected to it. We're going to filter on February 7th. And we're going to filter by snow depth here. So type, excuse me, type equals depth. We're going to ask for all of the columns in point data here. We're going to filter by that type thing. And we're going to filter again where the date is only equal to our collection date. We're going to limit it to just a couple thousand to, well, in this case, we're limiting it to a couple thousand to avoid overquerying the database, but we've already done that apparently. So these are just really safeguards for trying to do this as a group. And then we're going to convert that query into a geo data frame. And that's what this function does. So we pass it our query object, and we give it the engine object that we pick up from here. And then I print out how many records were returned. And in this case, that's 304. To plot this is, like David showed, it's not super complicated. A lot of this stuff is really just labeling and making it look pretty. You could get away with just this line. In this case, we're coloring by the value, which is the snow depth. And I picked a nice Pubu color map. So what this includes right now is all data that was labeled as depth in the point data table. And that includes several different types of instruments. So if we wanted to go and resolve this a little bit closer to, say, only things that were collected with manual methods, like the Magna probe, for instance, or the MESA 2, we can go and see what instruments are available on our filter. So like I said earlier, you can use this distinct function to help navigate some of your filtering questions. In this case, we're just filtering out all the data type equals depth and what instruments are there, and we want to see all the unique ones. And in this case, we get back MESA, Magna probe, camera, the pulse echo, and pit ruler, which is my favorite one. If we were to filter by point data.instrument equals Magna probe, we would be able to isolate this to just a single spiral, which is pretty cool. Okay. So we just went through a really quick example on how to access the snow depth data. And we introduced a new tool called Query to GeoPandas, and that lives in the SnowEx SQL library. And that's just a function to make your life a little easier and reduce stuff that people would do over and over again, just trying to get data out. The way we're going about this, you're probably experiencing some like shock in terms of just being thrown new stuff. So certainly ask some questions. Let's take like a minute again to ask some questions and answer them, and then we'll move on to some more advanced stuff. Oh, Mel says she's got it. So let's try it. No, looks like I'm still blocked out. That's a bummer. That's okay. It's not ideal, but it wasn't ideal when my internet went down too. So file not found. Jules is having a credentials issue. I don't think it was reset. Jules, are you trying to query locally maybe? Okay, she is on Jupyter. Yeah, I think Joe's right. I think we've just underestimated some of the settings on the database. So I guess we'll just hold off. Sorry about that. I really wanted folks to interact with the database, but it is what it is at this point. Okay. Are there any conceptual questions about forming that example and filtering on stuff, or anything that I could answer without querying the database? Okay, cool. Thanks, Jules. All right, so let's move on to some of these PostGIS functions. PostGIS is notoriously a well-documented software, and it's this extension that lives on top of SQL or the Postgres that allows us to have the GIS functionality. And in there is a bunch of functions that get mapped into Python and thus give us access to them. So we're going to explore a couple of those. I've only used probably 10 of them for the stuff that I've been doing, and most of those cover a bulk of my needs. They are pretty important for being able to use raster data, and that's the primary reason we'll talk about them. But we'll also show how to do some spatial querying with that. So just like before, there's also a handful of them listed in the cheat sheets that just helps you figure out that they exist and that they're useful. Just like before, we'll get our connection. We get our engine and our session object from this. Excuse me. And then let's pull a single raster tile. The raster data is stored in 500 by 500 pixels in the database, and it's stored in well-known binary format, which is not very useful to humans. It is super useful to the database because it's a little more queryable and it stores memory better. And there's just a lot of reasons to do it that way. So whenever we ask for a tile back, we have to convert it from well-known binary format to TIFF format. And there's a PostGIS function for that called st_as_tiff. And the general naming convention is st_ and then camel case, whatever the function is. So these are all written, like the documentation here is all for SQL, but we can take this and apply it in Python in almost exactly the same way. So we handed a raster object from the database and it'll convert it back for us the way we need it. Okay, so we'll import our table class here, and then we'll query the image data.raster. .raster is the column that holds each tile, and it's in that well-known binary format. And if we were to execute this, what we'd get back is this object called a raster element, which is just the library's way of holding that well-known binary format data. So if we want to use st_as_tiff, we have to import a new function from sqlalchemy.sql. And this is just giving us access to those mapped functions from PostGIS. We're also going to bring in another useful function which converts these data sets into something people are more familiar with, which in this case is raster.io or rasterio. And then we'll just bring in the plot function or the showing function. So we grab our session object. We're going to query that. We're going to use that func that we just brought in here and apply st_as_tiff from that function. And that's how that mapping occurs so that we have access to them. And then all we need to do is pass the image data.raster column to it. And then we filter, say, by type equals depth, which is the ASO data set that's in there. And then we'll limit it to one tile. We'll execute it. And what we get back is this list and result that holds the well-known or the as_tiff data sets. But it's still not very usable for us as users. So we convert it using raster to raster.io. And then we can show that data set just as if we had it read it from a file. And then you got to close those data sets. This is a really simple example, and it's only pulling one tile, and you'll pretty much never be using just one tile. So let's talk about some more PostGIS functions. To merge any tiles together, so if you know you're bringing back more than one, you'll use the PostGIS function stunion, and that will bring all those tiles and stick them together for you. The other thing, the other function that's pretty useful is st_intersects, and what this does is we can use geometry and say if any raster tile is intersecting this geometry, we want that as a filter. So let's try that around, say, some site. So we'll pick a site ID, and then we're going to get back the point data from that site. So there's some GPS location that's associated that's already cast into the right types, and that's what this query does. So we ask for the site data.geometry. We're going to filter it by our site ID, which is equal to this. We're going to ask for the distinct one because there was multiple times that we visited those sites. So we just want one of them. And that'll still be a list of a tuple. And so we index those that way. I would show these if I was just running these, but I don't have that right now. We're going to build our query down here. And remember, everything that goes inside of the query is what we want back or what we're going to get back. So we'll start by building this base variable, which we're going to put inside of the query. And this is forming the union of the raster data. And we're telling it that it is raster data, and I'll explain that in a second. And then we're going to apply the st_as_tiff to this chunk right here. And then we're going to query all that. So everything we want back is living in here. And so what we're asking for is we want a union of all the raster tiles that we're going to get, and we would like them as a TIFF format. And then we're going to filter by image data dot type, and then we're going to set it equal to insar interferogram real, and that's the real component of the interferogram. We can also filter it by the polarization, just so that we have a little bit less of a scope of data. And then we're going to say any of those tiles that intersect our point that we collected up here, so that's our pit, that's another filter we apply to it. And this just gives us the count. There's only one because we merged everything together. We'll convert that to raster IO data sets, and then we can just plot it. And just like that, we've got it. So there's a slight nuance here, and you're probably thinking this whole thing is nuance, but anytime there is a function that's used for different data types, like union, for instance, there's an issue behind the scenes with mapping. So SQL Alchemy is trying to map all these PostGIS functions to these, these calls here. Unfortunately, STUnion can't exist for both of them. So we use the GeoAlchemy version of Func to call this so that we can specify that it's a raster. That's a pretty small use case, but it's important because it happens with a lot of the rastering. You have to union it. Okay. So the difference there is that one of those STUnion in PostGIS is for rasters, and this is labeled as RT STUnion, but it's still used this way. And then there's an STUnion for just geometry, and that's why there's confusion there. Oops. Okay, so that's mostly focused on raster work, and there's a bunch of other PostGIS functions that will allow you to, say, grab pixels and everything else to do much more validation type analyses. But I figured we'd show a couple of examples, or an example with point data. So what we're going to do here is we're going to form a circle around a pit, and then we're going to ask for all the point data in there and then try to visualize that. So I just picked a random site ID, and I gave it a buffer of 50 meters. I'm querying that geometry column again, and I'm filtering by the site ID that we picked, totally random. You could change this if you wanted. And then we're going to convert that to GeoPandas just so it's really easy to plot. There's no other reason, really. It's a very small chunk of data here. But we also need that, that site geometry for our filter so that we can use it with the PostGIS functions. So we go, when we start to query our, when we want our buffered pit, we can use the database to build that geometry. So we go session.query, and what we're asking for is a buffer around our site with that buffer distance of 50 meters. When we do that, we get this buffered pit object back from the database, and then we can use that for filtering. So when we go to ask for our depths, we're going to ask for all the columns in the point data table. We're going to filter by the depths only. And then we're going to filter by instruments that land in this list. And so this is MagnaProbe and the MESA 2 measuring unit. And we're using this .in to use that filter. And this is just producing a Boolean list for us that says whether this row's instruments landed in this list. So this is just another filter by instruments. And you can do this with anything, but it's a useful technique. So when we execute that, or no, I do one more filter, sorry. We do PostGIS st within, and we're just saying the point data's.geometry. This is the geometry of the pre-built object for us, and whether it's in our buffered pit. And that's what we got from the query up here. Then we can cast all that into a GeoPandas data frame and plot it. And we get this excellent spiral. This is one of my favorite things, I think, is looking at these spirals. There's a lot of spirals that were done on Grand Mesa, and they're all really cool. Okay. So the goal of this here was to try to expose you to PostGIS functions and how to try to use them in Python. There's a little bit of a nuance when it comes to using STUnion because there's a raster version and there's a geometry version, and they're very different. But to use them, we have to go to different libraries to access them. And then you should be able to look at this and see how we can chain together some of these commands. For instance, up here, when we asked for the union of the raster data and we asked for it in the TIFF format, what we're doing is wrapping those two PostGIS functions. You can continue to chain those as long as the arguments make sense. OK. Another rapid fire session there. Are there any questions about this stuff? Let's take a couple of minutes and I'll watch Slack here. Oops, of course I can close out of it too. Yeah, I'm definitely, Megan said we could maybe do some breakout rooms later so that we could practice some queries. Definitely open to that if folks think that would be really helpful. I know it's a little tricky not having the database to actually practice this stuff on. The .limit1 is just reducing our query to one record. So whatever we ask for, it's just going to give us one back of that. That's a really good tool for building your queries to avoid accidentally pulling 3 million points, which definitely can happen because the GPR data set's about that big.
I assume it just grabs the first one in the list, or will it always be a random one?
I think it's the first index of your filtered data. So I'm assuming it's the index ordered.
OK.
Yeah, sorry, it's not working. That's just the situation we're in, I guess, at this point. If it makes you feel any better, my lights keep going out. So I don't know if that would make you feel better. OK. I don't see anybody typing, so I'm going to try to move on. A couple of last things here is exporting data. David talked about how to pull data out of GeoPanda data frames already, so I'll leave this example up for that. The good news is, excuse me, the good news is you can export those to a CSV or you can export it to a shapefile. Either way, that functionality is built in here. That's a great way to get a data set off of the database if you don't want to mess with this. You can also do this with rasters. And just like I was showing before, we can use raster to raster IO and apply those and then just save that as a TIFF. It's a little more complicated, but only because we have to carry the metadata that comes with it to the written file. OK, not a lot there. And I'm happy to answer more questions on that. But I figure most people will probably go back to this just to see how it's done. OK. You can use this with QGIS, and it does plug in very nicely. I've written up some examples on how to do that on the read the docs for the software. The examples do require you to understand some SQL statements. So you'd have to, here, let's go and click on those. So you'll get opportunities to do queries like this in there. I think I have these broken out by step so that you know how to add some of the layers. These are pretty handy, and it's really nice for making figures. That's about all I do in GIS user interface type stuff is make nice figures. But I'm sure you could, all that functionality for doing analysis does exist there. And it does work for ArcGIS, but I don't have a license for that, so I've never actually tried. But I do know that that functionality exists. OK. The last thing I want to really end on here is that this is an open source software project, which means that you can contribute. So if you have a data set that you want on there, even if it's not published yet, we can put it on there and leave the DOI as none, which just means that it's not been published yet. And then, anything that you see on the database as you're poking around, maybe it doesn't make sense, or maybe it's missing stuff. This is our database. And the good news is that we get to decide on what data lives in it and what it looks like and whether it's usable. Okay. So certainly look at contributing. You can make examples if you want, or you can make upload scripts, or you can just make issues. Any of it is for varying degrees of skills. You can work locally. Right now, the database is open to the world. So you could go and install just the Python package and do all these exercises locally and pull data. Finally, I just want to say thanks to everybody who's gone out and collected all these data sets. They're pretty awesome. And I participated in a little tiny bit of the SnowEx data collection. But I know that there was a lot of long days spent collecting. I mean, 30,000 manual depths is not collected easily. I wanted to say thanks to HP Marshall, who gave me the chance to do this about a year ago. You should, if you ever see him, you should buy him a beer, or better yet, volunteer to do some of his field work, because that's where he's at most of the time. Thanks to Anthony and Scott and Don for helping me deploy this. There was a lot of details that I was unaware of as we were heading into this back in the spring.